3, which is to understand the mechanism of skeletal muscle contraction. And here we're going to move on to talk about things like the sort of a bigger picture. We've talked about the fine details. We've talked about the contraction. We've talked about the filaments, the proteins, and how those things are regulated with calcium. We're going to sort of zoom out a bit and talk about the muscle on a whole and how we look at contractions in terms of units, which we refer to as the twitch. So we're going to look at the twitch, which is a single unit of muscle contraction per action potential. We're going to talk about factors that affect the force generated from an individual muscle fiber. So what are things that can increase the force generation? What are things that can decrease that force generation? We're going to talk about regulating the force generation of the entire muscle. And then lastly, we will talk about the velocity of shortening. How quickly can the muscle contract and how does that change? Let's begin by defining the twitch. So a twitch is a contraction that is produced in a muscle fiber in response to a single action potential. So what does the muscle look like? What happens on the muscle in terms of actin and myosin in response to one action potential? Now, this is an all or nothing event for a muscle fiber when it's at rest, right? So this can either happen in full or not at all. Very similar to what we describe for an action potential in general, right? Even on a neuron. Now, this can be in response to a single muscle fiber receiving an action potential, an entire motor unit, which is multiple fibers receiving an action potential, or an entire muscle belly, right? For example, the entire biceps receiving an action potential. So we can think about the twitch for a motor unit, for a muscle fiber, or for the entire muscle itself. Now, we can divide the twitch into various phases depending on the internal cellular events that are happening. The first phase is the latent period. And this is the phase where we have no force generation yet. So on this graph, we're looking at tension, which is another way to say the amount of force generated when that muscle contracts, versus time, right? And that is in milliseconds. So when we receive that initial stimulus, or that initial action potential, we're not going to immediately see tension or force rise because it takes some time for excitation, contraction, coupling to occur. It takes some time for calcium to leave the SR, to flood the sarcoplasm, to bind to troponin, to drag those tropomyosin thread proteins, and to expose the binding sites for that contraction to begin. So that is the latent period. It's the time that it takes for the machinery to get warmed up and for the regulatory proteins to actually engage actin and myosin and for the contraction or cross-bridge cycling to begin. So that is the latent period, and that lasts about a few milliseconds depending on the type of muscle. For contraction, this is where we begin to see force generation rise, and this is where we have actual or active cross-bridge cycling. All right, this can last anywhere from 10 to 100 milliseconds, again, depending on the exact type of muscle. If it's a small muscle, like the ocular muscles, or if it's a big muscle, like the hamstrings, right? That will be determined by the size of the muscle, the length of the contraction. So we have active cross-bridge cycling happening, and that is our second phase. This is where the force generation peaks. Now, the relaxation phase is where we have the reuptake of calcium. So the calcium ATPase pumps are pumping calcium back into the SR. This is usually longer than the contraction itself because this takes more time. And this is where the tension or force is dropping off. Again, this will happen at different rates depending on the muscle, but it is usually longer than the time it takes for the muscle to contract. All right, so the latent period, things are getting warmed up. The contraction phase, we have active cross-bridge cycling. The relaxation phase, we're trying to remove that calcium and pump it back into the SR, and the force generation is dropping off. Okay. And here's just an illustration of that. I encourage you to practice drawing this out. And I did add here just a little detail that this is in response to a single action potential. So what are the phases that we see after one action potential? And that is what we describe as the events of a single twitch. Now we can have two different types of twitches depending on what's happening with the muscle fiber itself. We can have isometric twitches, and isometric here, we can dissect this term to mean same. Iso means same. Metric means length. So in this instance, the muscle never shortens. An isometric contraction is where the muscle never actually shortens. And we'll look at what that means coming up. Isotonic twitches on the other end, iso again meaning same, tonic meaning force or tension, right? And so this is where the muscle does shorten, but because it has generated enough force to overcome the load in question, now the tension levels off, and so we have a steady amount of force being generated. So we'll look at what those mean, but two different types of contraction can be described when we look at the various types of twitches. Now, in order for us to look more at that, let's think about some of the different components of the muscle here. So the contractile elements are called the sarcomeres. These are the parts of the muscle that are actually engaging in cross-bridge cycling or contraction. The series elastic elements are the non-contractile parts of the muscle. That is the tendons, right, which are what are attaching the muscle to the bone, or even the connective tissue, such as the perimysium, which is the outer connective tissue wrapping on the muscle. That layer doesn't actually contract, right? Just the muscle itself will contract. We also want to think about the terms here. So the tension, we describe that as the force exerted by a muscle that is contracting, and the load is the force opposing that contraction. So a very practical example, if I'm trying to lift a load, that is the opposing force to the muscle that is contracting. So my muscle has to generate enough force or tension to actually overcome the weight of the item I'm trying to lift, and that item will be considered the load. Okay, so it's two opposing forces, the force generated by the muscle as it contracts, and the force opposing that by the weight of the object that you're trying to lift. All right, now on that basis and thinking about those terms, let's talk about the isometric twitch first. The isometric twitch or contraction is where the length is constant, right? The length of the muscle fiber remains the same. What is changing is the contractile elements, the non-contractile elements, or the series elastic elements. In other words, the tendons, all right? So the contractile elements are contracting, but they're not shortening. They're generating tension, but the length of the muscle fiber is not changing. What does change is the stretch that's happening, the elasticity that is being stretched of the tendons that are attaching the muscle to the bone. But the muscle itself does not shorten, and the load itself is never lifted. Now, in the schematic example that we have here, we've got a muscle that is suspended to mimic what the muscle would look like in the body, right? It's suspended across two bones. And we also have a force transducer, which is mimicking a load, right? A load that we're trying to overcome on the other end. We also have a simulator, which is mimicking the motor neuron that is giving this muscle the motor impulse, right? The action potential or end plate potential. So this is an exact simulation of what a muscle looks like in our body. In the relaxed state, we can see that this is nice and stretched out. okay? In the contracted state, after we have an action potential elicited here, notice that the muscle itself, the load is never lifted, the muscle contracts. We can see that there's contraction happening as there's shortening happening of the individual sarcomeres, right? But there's not enough tension generated to actually lift the load in question. What's happening instead is the series elastic elements or the tendons are stretching to sort of overcompensate because enough tension is not being generated to overcome this load. In other words, the load is greater than the tension and the muscle length remains the same. All right. Now, if you look at the amount of tension generated, it's going to increase. The latent period starts, the tension increases, and then it peaks, and then it drops off. It never actually flattens out or levels off because there's never enough to overcome the load. Let's compare that to an isotonic contraction or a twitch. Here we have a constant amount of tension because there is a point in time where we do generate enough tension to overcome the load in question. So again, looking at our experiment here, we have our muscle suspended. When it's relaxed, it's stretched out. Here's the load. Here's that motor neuron sort of simulation. Now, in this instance, when we stimulate the muscle, the load is eventually lifted because enough tension is generated that it exceeds the weight of the load and we can actually overcome or lift the load. And if you look at the muscle itself, it does shorten, it does move, and the load itself does move as well. Now, when we think about the tension here, we have the latent period to start, we have the contraction phase begin, and now because we've gotten to a point where we're generating enough tension and we don't need for that to increase any further, this eventually levels off or flattens off, and this is where we get the term isotonic from. In this state, the tension or force is the same because it is enough to overcome the load. And then eventually that would drop off. Okay, now we also want to see the degree of shortening. So shortening is actually happening as opposed to isometric contractions where there is never actually any shortening of the muscle itself. Okay, there's just stretching of the tendons, contraction of the muscle, but no shortening of the entire muscle. I do want to say here, and just to add, we'll talk about this going forward, but just to add it here while we have the illustrations, the isometric contractions usually precede isotonic contractions. So this is true even in everyday life. If you're trying to lift something heavy, let's say you're trying to lift, I don't know, a box full of books or a bag full of groceries, there's going to be a point in time where you're beginning that contraction with an isometric contraction because you haven't yet generated enough tension to lift that heavy item. So as you begin to try to lift it, your muscles will be contracting isometrically, so this instance, first, where the tendons start to stretch, the muscle is generating force, but it's not enough yet. And so that contraction starts out being an isometric one. Eventually, if you're in good enough shape or good enough condition, you will generate enough force to overcome that load or that heavy item. And so you will convert those contractions to becoming isotonic as you eventually lift that heavy load. So while we think about these as two separate types of contractions, in actuality, most contractions start out being isometric and then they become isotonic. Right. Now here's an example just to compare those things. So here is our isotonic contractions. And this can go in the opposite way as well. Let's say you are lifting something. So here's your isotonic contraction. You have your muscle lifting a 5-gram load because you can lift that lighter load. Let's say you added 10 grams onto that load. And now, again, you have an isotonic contraction because you can overcome that 10-gram load. Let's say you add another 5 grams on, and now you have a 15-gram load. Again, this is a muscle that physically can overcome up to 17 grams. So anything under 17 grams, we're going to see, excuse me, isotonic contractions, right? Anything below 17 grams, we're going to see an isotonic contraction where the load is actually able to be lifted. And notice in all of these curves, we have flattening off when we get to the force generation that is required for the weight of that load. When we get to a 20-gram load, here is where we can no longer physically lift this load. So we're going to see an isometric contraction. Why? Because we never get to a point where we generate enough force to exceed that 20-gram load and actually lift it, because the maximum force generation for this muscle in question is only 17 grams. So while we think about the heavier loads, if you start out trying to lift a load that's very heavy, you're going to start out being isometric, and then you become isotonic. But if you start out lifting a very light load that you can actually easily overcome, and then you gradually increase the weight, you're going to start out isotonic, and then eventually you're going to get to a place where it's isometric and you can no longer lift that very heavy load. All right. So it's really important to think about how the isometric and isotonic contractions sort of behave together depending on the types of loads that we would try to overcome. Okay. Now, when we think about the normal muscle contraction or the twitch, we can have some purely isometric contractions. Again, if you try to lift something that's just impossible for you to lift, it's purely isometric. We can also have isometric contractions preceding isotonic contractions. But usually it's very difficult to see purely isotonic contractions. So isotonic contractions by themselves is very rare. Even if it's a load that is constant, usually an isometric contraction will precede that isotonic contraction, and then it will become isotonic, okay? So you will try to lift the load for a short period of time, and then eventually you generate enough force to actually overcome that load. Now, the load can change. The load can really depend on the limb positioning. And this is true especially in everyday life. If you're carrying a bag of groceries, for example, the way that your muscles will perceive that load will change depending on your body position. So I'm sure you've tried to carry like 2 big, heavy grocery bags at your side, and that feels like a much heavier load to your muscles. If you try to carry it maybe over your shoulder, that could be perceived as a different, weight or a different load. If you try to carry it maybe across your arm, that would be perceived differently. So your limb positioning and the change in that will also change how that load is perceived and the type of contraction as well. All right. Let's think about factors that affect the amount of force generated by a single muscle fiber. So what are the things that it can increase or decrease the force generation? Now, when we think about the muscle contraction, that is dependent on 2 things. It's dependent on the force generated by a single fiber, which is really a reflection of how many active cross-bridge cycles are happening. Also, the amount of calcium, that's not listed here, but the amount of calcium is another indicator of how much tension or force a muscle fiber is producing, because that is going to translate to more cross-bridge cycles, and that is going to equal more force. The second factor that determines the muscle contraction is the number of fibers that are contracting. So when you're lifting a light load, for example, not all of the fibers in my bicep muscles are actively contracting to lift a very light object, right? So I can think about how many of those fibers are contracting. I can recruit more as the load gets heavier, and so that in itself will depend or determine how much force the muscle is generating as it contracts. So the tension produced by a single fiber as well as the number of fibers that are actively contracted. We can also think about the frequency of stimulation. So that is another way to determine the amount of force generated or the amount of contraction seen in muscle. And we referred to this as frequency coding. So how quickly are those action potentials arriving on the muscle? That will also determine the amount of force generated from the muscle. And there are two mechanisms by which the amount of tension can increase. One is called TREP. And TREP is this idea that when we stimulate a muscle once, so these pink arrows represent a single action potential, right? So one action potential arriving on the muscle, we generate X amount of force. Now the muscle relaxes in between. Another action potential arrives, we generate more force, okay? The muscle relaxes. Another action potential, we generate slightly more force. So each time an action potential arrives, because it's in close succession, we slightly generate more force the next time around. This is called TREP. And so in this instance, because we're generating more force, the idea that explains TREP is that the machinery is already warmed up. So it's going to take less time the next time around if it's close enough in time. Okay, let me say that again another way. So because the troponin, tropomyosin, the receptors, those things just experience a contraction, it's going to take less time for the latent period, and it's going to take slightly less effort for another contraction to come along, and it's going to generate more force because the machinery is sort of already used to or warmed up from that previous contraction. Now, there will be a time where the muscle plateaus, and that is simply owed to the fact that we've reached the maximum force possible for this muscle in question. And I just want to quickly compare that to summation because summation is different. Summation is where we have an action potential arriving, and then because the length of time for the action potential is shorter than the length of time for the entire muscle contraction, we could have another action potential arrive before the muscle fully contracts or relaxes, and then now we can generate more force because the muscle has not actually relaxed in between.